So at this point, we'll move on to the next session, which is about open data and democratizing AI for health. I think we've heard a lot of content here as to we need to be able to think of diversity and inclusivity in all the data sharing efforts that we have. So the session will cover a lot of this context. And one of our first speakers, who unfortunately could not join us in person, but recorded a video for us, is Dr. Roxana Daneshjou, who's a clinical scholar in dermatology, and she'll be describing her work on creating a diverse dermatology data set. So her video will take it away.
Hi, my name is Roxana Daneshjou, and I am a practicing dermatologist and AI researcher. Today, I'll be talking about creating fair AI algorithms for clinical diagnosis and triage in dermatology. Imagine you're on a vacation at the beach, and as you are sitting and enjoying watching the waves, you suddenly notice this on your leg. You don't remember seeing it before and are concerned about it. So you contact your primary care doctor and ask to see a dermatologist. As it turns out, there's a several-month wait to get into the dermatologist. Or maybe you're one of the 3 billion people living in an area with poor access to any dermatological care. What can be done to help fix this problem? It's been thought that artificial intelligence tools could be helpful in identifying which patients are at the highest risk of having a lesion that could be a skin cancer. Now, I use this image of a robot doctor a little tongue-in-cheek. However, given the visual nature of skin disease and advances in computer vision and artificial intelligence, there is the hope that we could develop algorithms that would help a non-dermatologist identify which cases are most concerning for malignancy and which cases are less. In fact, this could help us then be able to identify who might need the most immediate care. But what if your lesion looks like this? In dermatology, unfortunately, there are biases in our educational materials, with dark skin tones often less represented. In a recent TED Talk, Dr. Jeanne talks about how skin disease in dark skin can often be misdiagnosed due to the biases in dermatology education. Now, we often talk about artificial intelligence or AI as a tool that could help improve our diagnostic biases. But we also know that there's a danger of encoding our existing biases into our algorithms. So, will AI improve our biases, or will it make it worse? We asked ourselves this question as dermatologists. The first thing we asked is, well, what is the current landscape of artificial intelligence algorithms and data sets in dermatology? We did a comprehensive review of 70 AI papers in dermatology and found that the majority of AI data sets in dermatology are siloed and private. This means that we cannot access the data sets used to build the reported algorithms. We can't see what's inside the data sets, and we cannot directly interrogate the potential biases. In this diagram, every inaccessible data set is a red circle, while every shared data set is a green circle. The purple squares represent a research paper. As you can see, the public data sets, which were in green, generate more data, more papers, which is one cool takeaway, showing that democratizing data actually leads to the generation of more research and more papers and hopefully new innovations. So since we couldn't actually access the data in the majority of cases to interrogate potential biases, we had to delve into these research papers and see what they reported. And we carefully cataloged how they described their data. What did we find? Well, unfortunately, we found that most papers, 90% in fact, did not report the skin tones that were represented in their data sets. In the few that did, we found that they either excluded or underrepresented dark skin tones. Additionally, we know from the public data that's available that dark skin tones are often excluded or underrepresented. So, how do dermatologists quantify skin tones? There is an imperfect scale called the Fitzpatrick Skin Tone Scale, which was originally developed to assess how easily somebody burns or tans. This scale has been co-opted by the artificial intelligence community to assess skin tone diversity in AI datasets. The scale starts at 1 for the light skin and moves towards 6 for dark skin. You may have noticed earlier that I called this scale imperfect. I called it imperfect because it does not fully capture the full range of human skin tone diversity. But it is often the scale that is used. There are many people working on validating better alternatives, including a recently announced scale from Google, but we don't have a well-established replacement yet. Looking at the entirety of the data, the lack of dark skin tones in the existing data sets for dermatology, we wanted to solve this problem. And the way that we wanted to solve this problem is that we wanted to help create a validated data set of skin images across diverse skin tones. To do this, we worked with a team of dermatologists and AI researchers to develop the diverse dermatology images dataset. The first release includes 656 well-curated images that cover the complete spectrum of human skin tones on the Fitzpatrick scale. Every image was labeled using a biopsy-proven diagnosis. And moreover, we matched images of light skin tones with images of dark skin tones on sex, age, benign or malignant diagnosis, and the time that the photo was taken. This matching allows us to compare how algorithms perform on light skin images versus dark skin images. So, one of the first things we did with this newly created data set was to then go and try to test previously published dermatology AI algorithms. What did we find? Well, on this chart, what you see is a performance of 3 different algorithms. The closer the curves are to the red line, the worse the performance. And what we found is that the previously published algorithms, which were reported to do really well at detecting skin cancers, had far worse performance on dark skin tones compared to light skin tones. Why did this happen? As I mentioned before, most of the data used for AI in dermatology likely does not include images across diverse skin tones. Our images, which did include diverse skin tones, helped us with being able to test these algorithms for biases. Identifying these biases is the first and an important step in trying to address and fix them. Increasing the number of images across diverse skin tones can also help solve the problem. It can not only identify the issue, but help be a potential solution. We found that if we then took some of these algorithms that had differences in performance between light and dark skin tones, and then tune them on a set of diverse data, we could actually close the gap, the performance gap, in identifying skin cancer between light and dark skin tones. So, As we work to make artificial intelligence more fair, we have this call to action. We want to see more sharing of images of skin disease across diverse skin tones that can be then used for both artificial intelligence training and to do testing. Because our ultimate goal is that we have algorithms that can tell us that both these lesions are concerning for melanoma, regardless of the skin tone. If you are interested in checking out our dataset, it is currently hosted on Stanford Center for Artificial Intelligence in Medicine and Imaging website and can be accessed through this QR code. And of course, as I mentioned before, this was a team effort. And so I want to say a big thank you to the entire team.
Okay, virtual clap for Dr. Daneshjou. Unfortunately, she couldn't join us today for the panel session, but I'd like to move on and introduce our next speaker. He's both an ICU physician and a scientist at MIT. And he leads the MIT Critical Data team. Their goal is to change the way medical knowledge is created and validated. So here to speak about the harm when health data is not shared, please welcome Dr. Leo Celi.
It's great to be back. I was here more than 50 years ago. No, just kidding. More than 20 years ago, actually, did my ICU training here. I wanted to start with just disclosure of research funding. So our group receives research funding from the National Institute of Health, as well as several industry partners. And I represent MIT Critical Data, which is a global consortium. Our mission is to put data and learning at the front and center of healthcare. We consist of healthcare practitioners, engineers, computer scientists, and more recently, social scientists. And we believe that data and learning are actually the best medicine for population health. It's not vaccines, it's not antibiotics. And we try to bring together these different disciplines in order to derive knowledge from data that is routinely collected in the process of care to understand health and disease better and in the local context. The consortium is led by our group at MIT called the Laboratory for Computational Physiology. Our flagship project is MIMIC. I hope that some of you have heard of MIMIC. MIMIC is the Medical Information Mart for Intensive Care. It was the first resource of this kind. It contains all the ICU that is obtained or collected for all patients admitted to the intensive care units of Beth Israel Deaconess Medical Center. It's now in its fourth iteration, and there has been a lot of improvements. Since 2020, we have started uploading medical images linked with the rest of the electronic health records, so not just the ICD codes, but the entire notes, the labs, and the medications that are mapped to the medical images. And then this year, hopefully by the end of the year, we will be incorporating social determinants of health. So all the variables that are mapped to the zip code will be available for people to include for their modeling. In 2016, we partnered with Philips. We were able to convince them to also share the identified data from more than 200 hospitals across the United States. So that is the EICU Collaborative Research Database. And long believing that open access to data spurs innovation and accelerates progress, anyone could apply for access to MIMIC and EICU CRD, as well as a few other databases that we have created and shared with the research community. All you need is a standard course on human subject research training, as well as you have to sign a data use agreement. So the data use agreement stipulates that once you finish the project, once you publish your manuscript, that you will share your codes and queries. You will share your notebooks so that other people can reuse and double check your assumptions, whether they are correct or not. So there's a system of quality checks that happens when different groups are able to look at the analysis that were performed in previous studies, and they could build upon those research too. And I think that this is actually our biggest contribution to the research community. The best part of our work is really becoming data ambassadors around the world. So we have been organizing what we call datathons, which is short for data hackathons, where we bring together clinicians, public health practitioners, computer scientists, engineers, and social scientists. And it would usually start with clinicians from local hospitals or medical schools pitching their questions. And then immediately the teams are formed, and then they parse that question into a study design, they perform their analysis, and at the end of the datathon, they present their findings to the group. And a majority of them would be published. So a lot of our research actually comes from the datathons. And we have organized close to 40 now, maybe about 39 datathons in 16 countries across 5 continents. This has demonstrated the value of data sharing. So we typically invite presidents of the hospital, CEOs, and they see the magic that happens when data is made available to as many expertise, as many perspectives as possible. So with Mimic as their inspiration, our partners in the Netherlands, in Korea, in Spain have also adopted the Mimic model and made their electronic health record data sets available to the research community. And we're working right now with our colleagues in Uganda, in Brazil, and hoping to also release their data sets to the machine learning community. So as mentioned earlier, our goal is to transform the way we create and validate medical knowledge. How are treatment guidelines established? So how do doctors here at Stanford treat diabetes? How do residents in Uganda treat sepsis in their intensive care units? The answer is the medical knowledge system. And the medical knowledge system is fueled by research. And at the top of the hierarchy of medical research, as you know, is the clinical trial. But we also know that the vast majority of participants in clinical trials are white. So in 1997, 92% of clinical trial participants are white. That improved somewhat. By 2014, that has dropped a little bit. It's now down to 86%. But just note that as of 2015, the 75% of the global population live in Asia and Africa, who are not represented in most of these clinical trials. So do we think that we will advance precision medicine with the use of genomics or artificial intelligence? Probably not if we continue to follow the way we establish medical research, if we continue to follow the experience of clinical trials. So for genomics, we know that 87% of participants of global genomics projects are of European descent. In the United States, Blacks would contribute about 3% of genomics data, while Hispanics weigh in at 0.5 percentage point, despite the fact that they represent 13% and 18% of the US population. And yet, every big tech, every healthcare entrepreneur, every healthcare institution, they're touting that AI is going to transform the way we deliver care. There's been a lot of interest from industry. In 2020 alone, Microsoft, Apple, Google, perhaps invested around $3.7 billion to disrupting the healthcare market with artificial intelligence. Do we have proof that AI is transforming or improving healthcare outcomes? Far from it. We hear horror story after horror story when AI is adopted and deployed into a real-world setting. This is a paper that came out a few months after the pandemic, where they reviewed all the publications that have used CT scans and chest X-rays to predict the trajectory of COVID. And they honed in on 62 publications and preprints, and the authors concluded that all 62 papers had very fatal errors in their analysis. And this would include not giving enough information about their training and data set, not providing confidence intervals around their predictions. So they said that at that point, it was all garbage. It was all a waste of effort. One thing that we tell our computer science students is that we don't do prediction just for the sake of prediction. That's not really machine learning in healthcare. What the task that we need to do is to augment decision making. And that entails understanding how those decisions are made by humans, because we know that the computers will learn decision making from humans. So if we don't understand how decisions are being made, if we don't understand the biases that go into decision making, then what we're going to be expecting is that the computers are just going to parrot all our subjectivity, all our prejudice. Indiscriminately bamboozling data into autoencoders and transformers is not likely to transform healthcare. In fact, we might be headed to failure when it comes to improving health outcomes using AI for two reasons. The first is that the ground truth is not fair. We know that electronic health record data is rife with societal biases. And if we are not careful, those biases are going to be baked into the algorithm. The second reason is that the people who are developing these algorithms are typically either ivory tower academics or they trained under ivory tower academics. And these are the same people who created and perpetuated the problems that we see now. So the people who are charting the course of science, the people who are charting the course of medicine, those of us here, those of us who are on the table, perhaps don't have the perspectives to solve the problem because we don't understand. We've never bore the burden of health and disease ourselves. And we really have to make an effort to bring in colleagues who truly understand what disease is and the impact of disease in their lives. This was mentioned earlier. I believe that so far this is our biggest contribution to the machine learning in healthcare research. So this was published last week, and in this paper, we were able to demonstrate that it's pretty trivial to train computers on how to identify race, ethnicity from the medical images alone without any clinical data. And we were able to replicate this across chest X-ray data sets, including CheckSpurt and Mimic Chest X-ray, a data set from Emory Grady, with really relative ease. And we were able to replicate this as well in other imaging modalities. What baffled us is we couldn't understand what it was learning or how it was learning it. So it wasn't explained by the disease distribution, that maybe all the blacks have pneumonias and they were just mapping the pneumonias to race ethnicity. It wasn't explained by the bone density, which you could glean from the X-rays. It wasn't based on some specific anatomical region. And it also wasn't a specific spectrum of the image. So why do we care that computers can identify sensitive attributes such as race, ethnicity, or sex, or other demographics, even when this information are scrubbed from data sets? That brings me to the story of Clever Hans. Some of you might be familiar with Clever Hans. He was an Arab stallion. In 1900, he was bought by this retired schoolmaster named Wilhelm von Osten. And von Osten was bored, so he started training the horse to read numbers and also to perform some simple calculations, multiplication, subtraction, addition. And he got so excited because it seems like Clever Hans could actually really get the answers right. So he went to do road shows to he was so proud of the horse. But it turned out that the horse wasn't performing the task. It was detecting the heart rate of von Osten and the audience around him. So every time von Osten would point to the right answer, he gets excited. Everyone gets excited. The horse actually senses it. And he said it would come up with a neigh to say that that is the correct answer. When they blinded von Osten in the audience to the question, and then there's another set of audience watching it from afar, it turns out that Clever Hans wasn't clever. Like, all the answers were wrong. Are there examples of Clever Hans in machine learning? Absolutely. So these are two investigators from UW and UC Irvine. And what they did was to train an algorithm to differentiate wolves from huskies, except that all the photos of wolves had snow in the background, and all the huskies did not have any snow in the background. And very quickly, the computers learned that if there is a snow in the background, it's a wolf. So this is what we mean when they start using features that are not related to the task for classification or optimization or prediction. And we think that this is going to happen if the computers can tell whether you're LGBTQ, whether you're Black, whether you're incarcerated, whether you have behavioral problems, even though we try to hide that from the computer. So this was presented earlier by Sarah. It's been more than 5 years since this paper from ProPublica was published. And what have we achieved in 5 years? Nothing. All we realize it's very difficult to prevent AI from perpetuating societal biases. And of course, this is not very far-fetched to think that if you're using real-world data and you're not able to tell the computers which decisions are biased and which ones are not, then the computers are all going to absorb whatever is found in the electronic health records. Given the high-stakes consequences of an incorrect decision, it is very important that we use a very diverse data set. And as explained earlier, that's not happening at all. From a global perspective, the data sets that are being used to build and validate the algorithms are coming from a handful of countries. And 40%, in fact, of publications in AI in healthcare use data sets from the United States. Artificial intelligence has divided the world into data-rich and data-impoverished countries. So, where are we? I don't have the solution to all the problems that I presented to you today. But I could tell you that building algorithms with only a few of us being represented on the table is probably not going to do the trick. We have to really make deliberate effort to make the community much more diverse. And diversity is not getting someone from Stanford and MIT together. That's not the definition of diversity. It's really reaching out to our colleagues in minority-serving institutions, colleagues in low and middle-income countries to join us in this journey. And with that, I'm going to pass it on to the panel.
So again, this is the panel on democratizing AI and open data. And we have two very special guests today. So the first is Dr. James Zhou. He's an assistant professor of biomedical data science at Stanford and has been working on many innovative machine learning algorithms to study human diseases, and has also done a lot in terms of democratizing data sets for machine learning. Our second guest is Dr. Matthew Lundgren, who's well known to many in the medical AI community. He's a physician scientist and actually former co-director of the Stanford AIMI Center. He's now the principal for clinical AI and machine learning at Amazon Web Services, worldwide public sector healthcare. So welcome, Dr. Lundgren and Dr. Zhou and Dr. Celi. Yes. Okay, I guess that I'll start off with the first question. So continuing the conversation that Dr. Celi had started, I mean, we know that there's a problem, obviously, with representation, but how can we better address that? I think, certainly one thing is to have more people of different diverse backgrounds, right, working in machine learning, but are there any other sort of practical things we can do to increase representation?
I mean, from our perspective, I think one of the things we learned, this has all been a pretty experimental science, so to speak. We've tried to make data sets available. We knew that, at least in the interest of transparency for the work that we were doing, we wanted to show the world, hey, you can also do this. Here's the raw materials to make it happen. A lot of this stuff that has come to light wasn't known to us, at least we hadn't considered it. And I think it's because we made it available that we're able to look into these things. But one of the things that we've also learned is that in other areas, this isn't just a medical problem, right? Bias is a problem in a lot of machine learning. Making it very clear what's in your data in terms of breakdown from demographics, what biases may occur from models. There's been a lot of work done, I think from the Duke group especially, looking at how do we better inform users of either the data or the model to understand where all those blind spots could be is a great start. I mean, we can't necessarily mandate that data be shared by everyone. But I think there are growing efforts from places like the World Economic Forum, the UN, certainly the NIH, right, recently has said, in fact, any of you who are NIH funded would know that starting in January of 2023, you're going to need to share your data. That's 300,000 researchers around the country that are going to need to figure out how to share their data and do it in a way that's meaningful for the rest of the research community. So I think we're making progress towards that, but I don't think there's any one step that I'm aware of that's really been able to increase the diversity. Yeah.
Yeah, I agree that data sharing is definitely a really important component of this. I think in parallel, thinking about how to make models more shareable is also a very important and complementary component. Right? Because right now, if you think about what it takes to actually work with these machine learning models, so you have to do some coding, you have to have a fair amount of compute space, and you have to be able to actually technically work with training and to evaluating these models, which is oftentimes a fair amount of overhead. Right? So one of the big initiatives that we've been pushing on, in addition to data sharing, is thinking about how do we really make it extremely easy to share models, right? So that people can just work with these machine learning models, interact with them on their web browsers without having to write any code and without having to download anything. Right? So we created these platforms like Gradio, which is recently acquired by Hugging Face, which is basically a platform to make it very easy for people to share all sorts of machine learning models, especially for biomedical machine learning models. And I think one benefit of that is that when you have just very easy interactive interfaces to all sorts of models, then you can interact with it in real time. That just makes it a lot easier for much more diverse communities, non-computer scientists, to be able to debug these models, to gain trust in these models, because really the best way to gain trust is by tinkering with these models interactively.
I'm just going to add, which I alluded to this earlier, that we need to recruit social scientists to our team. We don't understand this as much as they do, and I think it's going to be important for every machine learning group to have at least one expert on the social scientists to join your team. Another thing that we tell our students is that before you even start doing your EDA, your exploratory data analysis, you need to do your homework. You need to know where are the disparities in that domain that you're planning to build an algorithm on. Because if you don't understand who are the marginalized populations and what are the drivers of those disparities, chances are you won't be able to detect them in your algorithm. And just to even promote further the data sharing, which I really think would be a solution to this problem, we were comparing the investigators who have used Mimic and other similar publicly available data sets, compare that to publications where access to data is limited to internal investigators. And we were able to show nicely that there were more women who are using our data set. There's better representation of different disciplines as well as different race, ethnicity when a database is easily accessible compared to when it's only accessible within Mass General or Brigham. You tend to preserve the order. It's primarily the white male professors who will be publishing off those data. So I think that this is maybe an intended consequence of open data sharing is you actually diversify the research community by doing so.
And do you think that, well, maybe Matt can answer this question because you're from industry now. But is there a role that industry can help, right? Or at least, those with a lot of money, right? Because I would imagine, as Leo had mentioned, right, a lot of this research is taking place in, ivory tower institutions. And the patients who go to those institutions, probably the majority are Caucasian, for example, right? So why don't the tech companies who have a lot of money maybe pay patients of racial and ethnic minorities, right, to, well, this gets into another question, who owns the data, right? Do patients own the data? But for example, let's pretend if patients own the data, is there a role for tech companies to pay patients of underrepresented minorities so that we can collect more of their data and those can be used to develop models that help those particular patient populations?
I hadn't thought of that. No, I mean, that's, I think from the sort of, and this is industry agnostic, I'll make a statement, industry agnostic here. I think that there have been a lot of efforts to make open data more accessible. So in other words, you guys are familiar with the Imaging Data Commons, potentially from the NIH. I mean, that's hosted on Google Cloud. It's going to be hosted on other cloud platforms as well to try to just increase the access. Now, along with that are a lot of very low code or very nice free tier offerings that allow computer scientists to interact with that data potentially even without having to pay anything. But in terms of trying to, I guess, seed the market or try to bring forth more diverse data sets, I'm not sure where that fits in terms of both the ethical aspects of it and then, of course, the economics of it, I think they would be challenging.
I was just going to say that that's not the solution. So having representation from marginalized populations definitely will help, but it's not going to address the disparities that exist in the data itself. So even if you bring in more Native American data into the data set, they will keep having poor outcomes because of so many reasons. It's not just access to care, it's also how providers see them. So unless we understand this, we couldn't lump them all under bias. I think that's gonna be wrong to just say this is all bias. We need to dissect that. What proportion of the bias is from subjectivity of the providers? So what proportion of that is because of unequal access to healthcare? What proportion of that is due to digital literacy of the different population groups? Because if you don't understand that, as I said, I think we're doomed. I think all our multi-billion-dollar investments on healthcare AI is not gonna go into something that is going to improve population health. And until we figure this out, I think that we should pause about federated learning. I have been very vocal against it just because I think that there's a time for federated learning, but that's gonna come after we figure out how do we prevent biases when we see all the data in front of us. How do we prevent these algorithms from perpetuating any disparities that we're seeing now?
And I'll just follow up on one point Leo mentioned, which is I think is really important, is that just the notion of bias itself can be very complex. Right, you can see an algorithm having disparate performance across two populations, and that might look like bias on the surface. But if you look more deeply, there could actually be more like mechanistic or more causal factors. Maybe it relates to how the data is collected or the kinds of equipments used to collect the data that actually explains that disparity. Right, so I think that's a big part of the challenge is to think about deeper ways to audit the data sets and to audit algorithms, oftentimes requiring access to more metadata on how the data is collected and generated that can really try to drive at like what are the root causes of the disparity in the algorithms.
And I'm just gonna call us out. Here we are, 4 very privileged individuals talking about bias. Like how wrong is that? But anyway, back to you.
Well, it looks like we have a burning question from someone who's been standing longer than a surgeon in a long operation, so please go ahead.
Thank you so much. I have a question regarding to data collection. Do you think that the religion and culture is a barrier for collecting data, especially in developing countries? And what would be the engineering solution for these issues?
Personally, I think it's politics and economics. It's not technology. It's typically politics and economics. They don't want to share. They think that you're going to find some poor quality of care. If you start looking at their data, they say that the data quality is not good enough. They give you all the reasons. And I tell them it should not be. It will never be perfect. If you wait for your data to be perfect, it's going to be useless. That's going to rot away. You better share what you have now. And then in the process, you will actually be able to improve your data collection because you realize how valuable the data is. And then, of course, economics, they could sell this to IBM. They could sell this to Flatiron. So why would we share the data? So to me, that's very problematic. What people don't realize is that this data is useless unless it gets curated. I don't even know how markets can curates their data or Flatiron. Can we trust their curation? Because the curation is not open. We don't know how they merge concepts from across different systems. And I'm just skeptical of the models that are coming out using that data if you don't know exactly what assumptions they had when they combine data coming from different health information systems. But it's politics and economics. If we could address that, they always think it's technology, so maybe Terra will be able to solve this. Like, nope, it won't solve the politics and economics issue.
Thank you.
Certainly. Another audience question? Oh, I'm sorry. I ignored the right side of the room. Please go ahead.
So I have a question about open data, and this relates to, so we're participating in the AIM Ahead consortium. This is a national $100 million initiative to make data sets openly available, to do data science training with a lot of HBCUs, Native communities, and through that program, we've been kind of building capacity programs with the Alaska Native Tribal Health Consortium. So this is just one example of an organization that has a very rich history of data collection, of its own kind of healthcare delivery system. And they are very keen on using data and building capabilities internally. I am curious, how do you, because when data is made available, there are individuals and institutions that have much lower barriers to effectively using it. So I see opening data as removing one barriers, but the communities that have been marginalized are much more poorly positioned to effectively productize that data into things that can be valuable. So to me, opening data is just, I don't know if it's the full problem, because I feel like you have to do the capacity building as well to actually build equity in how people use their data. So I'm just curious, like, I think that's one example to me that makes a whole lot of sense, where the driving force is not actually opening the data, but it's a different type of approach to capacity building. I'm just curious how y'all think of it, especially working in other countries too.
So it's both for sure, and a large chunk of our initiatives is capacity building. So we partner with institutions in other countries and making sure, so I hate the term upskilling. It's not upskilling because you learn something from them. You learn the perspective. So we call it cross-pollination. We have this concept of village mentoring and hive learning, where we try to bring together different labs to share their students, share their postdocs, have common journal clubs and lab meetings. We partner with labs in Asia, in South America, in Africa. And I think that needs to happen too. So it's not just data sharing. That's not going to be the panacea for this problem, but definitely building capacity across countries, across populations would be a requisite to achieve our goal.
A question from the polite gentleman over there.
Hey, my name is Varun from Curai Health. I know in Dr. Celi's presentation you had a lot of examples of failed integrations of systems. And so thinking about from a bias perspective, how do you think about the standard that we should be holding algorithms to? Is it fair to hold algorithms to a standard higher than that of clinicians, knowing that we know clinicians can have biases of their own? And is it okay, at what point do you think it's okay to integrate systems into care, provided that they may have some higher value add, but still some implicit biases within them?
So my dream AI is an AI that will alert me that I might be having a biased decision. Like at 2 a.m., maybe I'm hearing the accent of the family that I just talked to, so I recommend that we withdraw care. At 2 a.m., maybe I'm seeing the color of the skin of this patient and would say that we should not offer this treatment because the prognosis is really going to be poor. And we don't know quite yet how to do that, but hopefully that will address some of the problems that we're having now. But you're perfectly right. Why are we holding AI to a higher standards compared to humans? I still think that AI is the way to go. Computers are much easier to audit. Computers are much easier to recalibrate. You cannot recalibrate doctors. You cannot, it's very hard to audit doctors either. So I think that this is the way to go, but we have to be more measured in terms of what we promise to the world in terms of capabilities of AI as it exists now.
Yeah, it's easier to debias algorithms than to debias humans. And I think part of this is also like the ways and metrics to evaluate algorithms should be different from how to evaluate human clinicians. Right? So for example, for algorithms, I think it's actually really important to do more continuous monitoring of these algorithms over time, rather than like a one-time FDA approval, one-shot evaluation. Just because the nature of a lot of these learning algorithms is that the data can change over time. The models also drift over time, right? So the more the continuous monitoring frameworks will be more applicable.
All right, it looks like we have one more question. I think we'll make this the last question.
I think she was first.
Oh, I'm sorry again. Bias in action right there. All right, please go ahead.
It's okay, I'll get over it. So I had a question on basically maybe algorithmic strategies to reduce bias. So like when we have imbalanced data set, we might try doing different data augmentation techniques, like maybe flipping an image, rotating it slightly, things like that. So looking at like maybe, you know, on a broader scale than that, are there ways to do data augmentation to try to fix some of these challenges, or maybe use generative models? I'm curious if anyone has been working on things like that.
Yeah, I think it's definitely a really interesting direction. So there's a lot of work, recent work on trying to improve the fairness of algorithms during the training time. So that can either be done at the data stage of doing data augmentations, can also be done at the stage of changing the objective function that's the algorithms being optimized for, right? So instead of optimizing for the standard aggregate loss or aggregate performance across the entire population, one approach, it's pretty promising to think about asking the algorithm to do well across all the subgroups of the population explicitly, right? So that somehow, even for the small minority groups, the algorithm is still working well. I think those are promising approaches, but there are definitely some limitations in how much we can achieve just by changing the algorithm and the training process itself, right? And other people have done a lot of studies of the form that, you know, we can use the most sophisticated methods of data augmentation and of the objective trained model for the models, but there will still be some residual intrinsic biases that's not addressed if we don't really go back to the root of the issues.
And one thing we could do is to really bring in the causal inference people. So I think causal inference has to be part of machine learning. We can't just look for association. We need to understand did this one really caused the other action or the change in the state. So definitely there has to be a marriage between machine learning and causal inference.
Well, and that, of course, comes back to the idea that, you know, that's more investment into your data set, right? If you really want to get all the way to pixel-based labels, you're actually forcing the causal association much more, you know, expensively, basically, right? It puts you in a position where, you know, you see these models that actually are based on very, very detailed annotations tend to generalize better than those that are, you know, right? And that, I think, is a strategy that, you know, again, is incredibly expensive, but ultimately may be able to scale better than trying to find a shortcut with the technique.
Okay, well, I think if you can make your question very quick, we'll do one loop through here.
Yeah, I actually
and
want
then
to be
conclude.
a little bit provocative here. So I'm Eric Esquiaga. I'm Executive Vice President, Chief Medical Officer of an $8 billion integrated non-academic health system. And one of the things, how many of you guys have heard of Truveta? Raise hands. Very little, which is amazing to me. So Truveta, 15 of the largest non-academic, not-for-profits have gone together and formed this for-profit organization called Truveta, and we send our de-identified data into that depository. It's been in process for 2 years. Microsoft invested another $100 million into it. Currently, we have 25 of the largest healthcare systems in the United States, and there's about 20% of the data in there. It's growing rapidly. What I'm surprised is there's still, you know, I looked at Leo's slide where he was showing the ivory tower. There's still that chiasm between a big difference between the academic medical centers and non-academic medical centers. And we don't see any academic medical centers joining in there trying to monetize the data. And we each paid $5 million, and Microsoft invested $100. It almost seems like we're going parallel track. You know, I was at Vanderbilt, I was a professor, so I understand it. But, you know, in academia, you guys see mainly the zebras. When you're talking about Ascension, when you're talking about Providence Healthcare, when you talk about Novant, when you're talking about Atrium, we see everything in between. Our population, our data set is much richer in a way, diversity-wise, than the academic medical centers. So I just want you to be aware of it, and I just want to be a little bit provocative about that. Thank you.
Can we make it publicly available?
It is. It's going to, well, it's not going to be publicly available. Now, it's available to me. I can go and look at the data of, if I want to look at Coumadin use, I can go and look at the data for Coumadin use and how the institutions are using, what populations that they're using, and how is it working in different populations. If I'm a member, I can look at it. Well, it's been around only 2 years. They just started it. So they have a couple of chief data scientists there that joined them from Microsoft.
You need a whole village of data scientists.
Yeah, they do have. And the team that came is actually the team that developed, and he had been there, Terry had been at Microsoft for 25 years. He was an executive that developed the entire Office product at Microsoft. So it's a very strong team. I believe, I mean, look, I don't have any money in it, so, I have no vested interest, but I believe they're going to be successful because they're for profit, and they get a lot of industry money coming into it.
So Mimic has 30,000 users, and we don't pay them any money to help us curate the data. And I think that's something that we really should do, is that curation is so difficult. So a small team of data scientists and clinicians is not going to do the trick.
Yeah.
It's so difficult to curate health data.
But look it up. It's called Truveta with one T on each end. Thank you.
Thanks.
All right, thank you. So wonderful panel. Thank you all again